Hi, my name is Angela Wynn, and today I'll be presenting on Lab 5, which is about the falling slinky. So the purpose of this lab was to demonstrate and predict the motion of a slinky that is dropped from rest, and to compare that to a computational model. An important concept is Newton's second law related to this lab, which states that the motion of an object is dependent on the net force acting on the object and its mass. Important formulas include the update velocity formula, where final velocity equals initial velocity plus F net over m times delta t, where F net can be calculated as the mass times acceleration, or here it is the sum of the gravitational, the drag, and the slinky forces. And the drag force is the object's speed times the velocity's direction. And here, the force of a slinky is associated with the gravitational and the tension forces at the top of the slinky acting on the bottom. Also, gravitational force here is equal to negative mg, where m is the mass of the object and g is the gravitational constant. First, in Tracker, I tracked the motion of a slinky dropped from rest, and the mass of slinky was 0.25 kilograms. And using Tracker, I extracted the initial position shown here, and the initial velocity would be 0 because it is dropped from rest. Delta t is 9.4 seconds. In Glow script, I edited these lines, so I extracted the position and I put it in here accordingly, as well as the mass, so the initial states of the slinky, as well as the time. And so here, this while loop represents when the bottom of the slinky is still motionless, and this while loop, the second while loop where t is less than 9.4 is when the bottom of the slinky is moving. Here I calculated the gravitational force and the tension force, and they are equal to each other. And adding them, they will be F net. And I also adjusted the velocity and the position update formulas accordingly, as well as have t equals t plus delta t to advance the loop. I did the same thing in the second while loop. Results. So this is a graph that I made showing the computational model results and the observed results from Tracker. And as expected, the position of the bottom of the slinky remains constant up until around the 8 to 9 second mark, where the top of the slinky reaches the bottom of the slinky. There is some deviation between the model and the observed results, especially near the end. Here we see an outlier in the observed. But I think this can be attributed to man-made errors made while tracking Slinky's movement in Tracker. So overall, we see that the Slinky collectively didn't fall until the top of the Slinky reached the bottom, where the tension of the coils are transmitted downstream. And once tension forces reach the bottom of the Slinky, they act on the Slinky as a whole, causing it to accelerate downward due to the gravitational force. Overall, I think the computational model was successful in modeling the Slinky's behavior. Thank you.